So it's important, if we're going to control sound, to understand how sound behaves when it interacts with another body, so some other surface or object. So if we think about the incident sound wave energy, shown in red here, and it's traveling through the air and it hits something, one of three things is going to happen to that incident energy. Part of it may be reflected, okay, and bounce off the object. Part of it might get trapped inside the material or absorbed. It's kind of shown in yellow here. And then part of it may be transmitted or go right through the object, and that's what we'll show in blue. So the green, the yellow, and the blue, those three parts summed up will give us back our incident energy. Okay, no energy is obviously lost in this process, but we're trying to control, through sound control, we're trying to control what happens to that energy. Okay. So if we move over to sound transmission loss, now we're talking about the sound energy that gets through our barrier or through our material. Okay, and again, it could be a muffler, could be a wall in our apartment building or something like that. Here, transmission loss is the logarithmic ratio of the energy that is incident to the energy that gets transmitted. Okay, so the way this is formulated, if we have a lot of transmission loss or a high transmission loss, that means there is very little that gets transmitted through, or the transmitted power is very low. Okay, so that's why this is in the denominator. High transmission loss is a good thing.
So this is kind of like absorption, where the higher the better as far as reducing sound goes?
Exactly. Yep.
Yeah.
Exactly.
But this doesn't go 0 to 1. It's
No.
a dB value in the end?
That's right.
The higher the dB?
Yep.
Okay.
That's right. So again, we could be talking about mufflers or an exhaust system and a duct sort of application, or we could be talking about a literal physical barrier like a door or a window. Okay. And if we plot the sound transmission loss, again, this is sound transmission loss in decibels on the y-axis. The higher this curve is, the better it is for sound reduction. Okay, so this muffler, you see this areas where it's very good, and then you see these areas where it drops off. And these troughs in the sound transmission loss usually relate to resonant frequencies of this, the size and width of this expansion can. Okay, so there's some frequency that fits perfectly in here, this way, and so those will be these frequencies that the muffler doesn't do a good job of blocking. For sound transmission loss, you notice we are going to use that same tube, but we're going to add on an additional little half here with two more microphones. Okay, so in this case, the sample is going to go sort of sandwiched in between our four microphones, and we've got our speaker at the one end. We're going to broadcast a bunch of noise, goes past mic A, past mic B. Some component might reflect off. We're going to quantify that using mic A and B. Some component might get trapped inside, but then some component of that sound energy is going to go through our sample, and we're going to quantify that amount with microphones C and D. So now we know all three parts: reflected, absorbed, and transmitted. What we're really after in this kind of setup is the transmitted part, and will allow us to calculate the sound transmission loss. Now this sample in here doesn't have to be foam or a barrier. It could be, like we were talking about, a muffler or an acoustic duct element. We would just hook it up right to our tube. Process is the same. For developing a muffler, we could have a whole series of expansion cans and different sizes.
Looks like you could maybe
inside.
fit an equation or something to that and be predictive. Instead of like having to test a bunch of combinations.
If only there was a
software somewhere in the world made by a great engineering company like Siemens.
Look at this.
SimCenter 3D. Wow. So yeah, you can set up all these chambers and everything else and tune it for the frequencies you need. And we have routines, already set up for you to help you do transmission loss. So you have inlet, outlet, and then you can automatically see the result of that. And if you have different porous materials and things inside there, you can do that as well. So it's not just a test thing, but it's also a simulation thing, and you get nice three-dimensional data here, which is another factor that we didn't kind of mention. We're showing a simple diagram like a 2D diagram, but really you want to do 3 dimensions, especially as you go up in frequency.
For sure. So those are some muffler applications. Some other ways we can control sound in terms of duct acoustics. One of the tricks here is something called a Helmholtz resonator. And this is an additional acoustic volume that you put on your duct to try to control noise at a specific frequency. And if you're familiar with a tuned mass absorber from a vibration standpoint, you know you have a mass and a spring tuned to a specific frequency. This Helmholtz resonator is exactly the same principle. We have a mass, which is the amount of air that's in this sort of neck region, or we call it the mouth here. And then you have a spring, which is controlled by the volume of air in the branch that you have attached to your parent duct. This will set up a single degree of freedom system that will oscillate at a specific frequency. And by definition, that frequency will be, or that resonance will be 180 degrees out of phase with the parent structure. And so we get this dip, drastically knocking down the amplitude of a single frequency. Now you could place this any number of places on your duct, and like a tuned mass absorber, there are going to be good locations and bad locations. And you see the original sound pressure level versus frequency here is shown in the red. Okay, and we have this peak at about 350 hertz. Okay, and this is the problem we're trying to treat or control with this Helmholtz resonator. So we develop and design our Helmholtz resonator so that its natural frequency is right at 350 hertz. It's got some volume and some neck area here that will be the associated mass, so that it resonates right at 350 hertz. If we put it in the best location, we'll see this drastic reduction in sound pressure level at that natural frequency of 350 hertz. Just like a tuned mass absorber, we get two smaller peaks above and below in frequency, but right at 350 hertz, our problem is totally gone. Okay.
Yeah, so you just put it on an active spot, like that red area on the left side there, huh?
That's right. So this was a good location for our Helmholtz resonator because at 350 hertz, this is an area of high pressure oscillation, whereas something like the blue or the green, it's not going to be as effective because the pressure oscillations aren't as high there.
Makes sense.
Okay. Yep. So one of the other neat tricks you can play in duct acoustics is called the quarter wave tuner, or quarter wave tube. Here, it's a much simpler design. Again, it works at a single frequency. All you need to do is create a side branch. So this is the main duct here. This is our quarter wavelength tuner. And it's just a branch, some other place for the sound energy to go. But we tune the frequency by tuning the length. This length is 1/4 of the wavelength that we're trying to attenuate. Okay? And this will work for any odd number of quarter wavelengths. So 1/4, 3/4, 5/4, etc. all will have this same characteristic. Obviously, we most often use a quarter wavelength tuner just because it takes up the least amount of space and it's just as effective as all the other ones. But what this will allow us to do is use some deconstructive interference to our advantage. Okay, and we have a little simulation that's going to show you how this works. So you'll notice these high amplitude red and blue pulses going down the branch. This is our quarter wavelength tuner here. And you'll notice what happens. I'm going to rewind. So it takes a little bit of time. So the energy has to go down. It branches off, splits, and goes and sort of charges our quarter wavelength tuner. Now watch what happens when this sound energy bounces back. You're going to start having an area of red right next to an area of blue. And what happens is this sound energy goes down here, hits the end, and bounces back. And by traveling a quarter wavelength before it reflects, the phase gets inverted. So now we have high amplitude of negative pressure meeting a high amplitude of positive pressure, and they're going to sort of deconstructively interfere. And so you see the pressure pulses downstream of this tuner are all nice and green, sort of low amplitude, whereas they're red and blue are high amplitude going in. So I'll play this one more time. But watch what happens after the quarter wavelength tuner gets set up. These pressure pulses reduce in amplitude and they're just this nice creamy green. That's how a quarter wavelength tuner works.
That's nice.
You'll see these all over the place in the induction system in your car, even sometimes on the exhaust system. But again, they work at a single frequency, but there's nothing to them. It's just a little side branch. There's no moving parts or anything, so it's very effective.